So let me now, and I introduce the definition that we want. Okay, so let me fix the notation. G is a connected, reductive, or if you want sensible, real PV. And linear, I'm assuming linear always, so real points of something. Then it says A inside G is maximum compact. Theta is the involution, involution. G is K plus P is the composition given by K. And we have the notion of a theta stable parabolic. Yeah, I'll also fix maybe. If you want to use the mic. Oh, yeah. Theta is the Cartan involution, and we have the basic notion of a theta stable parabolic. So maybe later I might use a fundamental Cartan. So this appeared in Barsati's lectures. So this is it's a theta stable Cartan, and then you can separate it according to how theta acts by plus or minus 1. So here also theta acts by 1 here and minus 1 here. And you can separate it according to that. So this is the compact part, and fundamental means that the compact part has maximum dimension. Okay, so and it's a basic theorem that all fundamental Cartans are conjugate actually under K. Okay, so whatever we do with them won't really matter after conjugacy. And we had the notion of a theta stable parabolic, which is subalgebra. Which is one, so this is a parabolic subalgebra of the complex Lie algebra. So G and all that are all the same. G is the complexified Lie algebra of that G. And it has two properties. One is that it's stable under theta, as the name indicates. And the second is that if you conjugate it with respect to the real structure and intersect with K, this is actually a Levy. Is a Levy subalgebra. Okay. Now this is a Levy subalgebra. In particular, it's a subalgebra of G, so there is a corresponding. It's also obviously defined over the reals because it's stable under conjugation with respect to the real form. So it gives a subgroup inside G. Okay, and it's a basic fact that we'll use without this thing that L is connected. Okay. So if G is connected, then L is connected. If G is only connected points of the points of a connected real algebraic group, for example, Harishchandra class. So most of what I say will be true in Harishchandra class, but some small things might be off, but they can be fixed. But I'll just point out that if G is in Harishchandra class, it's no longer true that L has the same connectedness as G. L might be more disconnected, but one can get around it. It's again in the Harishchandra class, so everything works nicely. Okay, so what I want to point out, let me give one example of such a thing, just so that we have some. This is the Levy. Okay, so one example, so this is the same example that I explained last time. So G is GL2NR, of course. This is neither semi-simple nor connected, but I'll pretend as it is. Maybe I'll take the connected component necessary. And then if I take there's a natural choice of fundamental Cartan. Okay, so the natural choice of theta, or one good choice of theta is minus X transpose. Okay, this Cartan involution. Then the convenient choice for this is to take. This consists of matrices of the form diagonal of 0 blocks minus theta 1, 0. So 2 by 2 blocks on the diagonal with one parameter theta in each of them. This is just a real parameter. That's the convenient choice for T naught. For example, in SL2 or GL2, you just have 0, the span of 0, 1, minus 1, 0. And this guy one takes to be the diagonal span of, say, x1, x1, 0, 0, and blocks like this. Now, inside this, there is a natural element which is, maybe I'll call it, I take I times the thing with blocks 0, 1, minus 1, 0. Okay? So I'm just writing down this. So this is the n cross n, 2n cross n matrix with blocks 0, 1, minus 1, 0, like that, and then I. So this belongs to I times T naught in this picture. Okay? Then if one takes the stabilizer of that, of the line generated by that, okay, so I'll come back to this later, but I just want to fix this notation. This leads to the following, this gives a theta stable parabolic subalgebra, which is isomorphic to GL and C, and it sits inside GL and R, 2nr. And when n is equal to 1, this is just like embedding a plus ip inside as in this form. Okay? So in the general case, of course, you have n squared complex numbers and you want to put them into 4n squared real numbers, so you put them in 2 by 2 blocks like this. Okay? So this is one special theta stable parabolic. So it's not a real parabolic, but it plays a role in what we want to say. Okay, so before I start talking about cohomological induction, let me make one or two. Okay, I won't make it.
You don't want to find a parabolic, you have to find a levy.
Thank you. So this is the levy, theta stable levy. By which I will, that's not going to define, I just mean the levy of a theta stable parabolic. Yeah? Okay, so I won't define it. If there's more than one, you can go with this. Okay. So the basic construction we want to make, if you recall, is that, right, okay, so a general setup is that I have a theta stable parabolic, and this gives me a pair, I was going to continue this here. So I have Q and I have L, which I want to intersect with K. So I'll, just to save a little time, I'll write that as LC. I hope that doesn't cause any.
Yeah. Carbon that you're using should not be normally the carbon in that C. Like minus X transpose or
yeah, that's what it is.
But if it's minus X transpose, then how will you stabilize the parabolic?
I haven't defined the parabolic. It doesn't stabilize the ordinary parabolics. That's the point. So the theta stable parabolic is not a parabolic. So you make Raghunathan's objection to the a theta stable parabolic is a parabolic of the complex subalgebra, not of the real subalgebra. See, it's not placed, if it were a parabolic of the real subalgebra, then these two would be the same, so this could not be true. Okay? So in this case, I will
It's just as well to say it's just the eigenvalue 1 minus 1 for this. It is not for this GL and C.
yes,
You have defined the element and it is just the eigenvalue plus minus 1 for that element.
for this element, yeah, that's right. Yeah, so the eigenspace is plus minus 1 for this element. Okay, so just take the roots, the usual roots with respect to H naught, which is the same thing, which pair with respect to this element either positive or negative. If they pair 0, they are in the middle. Okay? Okay, so what I want to say is that I have, given any theta stable parabolic, I have this pair. Okay? So I might sometimes write LC for this pair, but I may not be consistent about it, but let's just ignore that.
I have a question. So it requires to the GLN to be even dimension. So
this requires GLN to be even dimensional. In general, you just put one large element something there, and you do the same thing. Namely, you take the root spaces on which have the real roots of GL to n plus 1 say, which are positive on this element versus negative or 0. The 0 will be the levy, the negative will be the conjugate of the root space because this is I here. And the positive, the U part will be the positive. Okay? Yeah. Okay. That's not all, that's not a complete classification, but this, what I just said, namely, I'll just say this in words because I don't have time to write it up. Namely, I choose an element of IT naught. Okay? Now take the, sorry. Choose an element of IT naught. Now take the roots with respect to H naught. Okay, and then you take the root spaces which are positive on that element that you fixed. This might be the element. The root spaces which are positive on the elements you fix will give the U part. The root spaces which are 0 will give the levy, and the root spaces which are negative give the levy of the conjugate. Okay, these two have the same levy, not the levy, sorry, the uniform radical conjugate. These two have the same levy by assumption. Is this clear? And that is a complete classification of theta stable parabolics for GLN, and it's obvious roots, weights, all these things work in general, right? So this is actually a complete classification of all theta stable parabolics. Okay, I'll come to that later. But the point is that you can enumerate them, it's completely elementary. There are some conjugacy statements involved. I already said that my choice of H0 is not a choice because everything is conjugate under add k. So once I fix that, therefore the final statement will be every theta stable parabolic is conjugate under add k to one of the form that I just described in words. Okay? Okay. So our basic aim, or at least we believe that we can do the following, is that we want to go from L intersection K modules to GK modules, right? So this is the category of GK modules that was used earlier. So of course the first step is to maybe go to, okay, so I don't have enough space here, is to go to Q, L intersection LC, okay? So that is you inflate trivially on N. Of course remember that you can also inflate with Q bar, so both of these would make sense. Then you can go to, from here, let's say, suppose we could define, I have to define a functor like this, that will take me to GLC, okay? One can imagine, okay, so I'll write this here also, so that one can imagine easy functors to define here, namely because Q is a subalgebra of G, UQ sits inside UG, so tensoring with UG is one obvious choice, right? Except that I may not be landing inside, I have to worry about whether I'm landing inside L finite vectors, okay? And the next step is something that I want to do, I might want to go from like that. So I'm just saying that if you want to construct functors from here to here, one way to do it would be to do it through a series of steps. The first step is trivial. The second step, well, there could be two things. You could tensor with UG and take LC finite vectors. Actually, tensoring with UG is enough. Or you could also take, there are two ways to go from, see, I mean, this is like a general situation of change of rings, right? So I have a pair of rings, and if I want to go from R modules, let's call this R, to S modules, I can either tensor up, or I can take HOM from S, R module homomorphisms from S into the module. Okay? So both of these, so I could take HOM over UQ from UG into my module, and that would give me a way for going from here to here or here to here. However, then again I would have to worry about L finiteness, K finite. So I would impose that condition on HOMs. I would take the K finite HOMs or LC finite HOMs. Then there would be the last step, which has to be thought about. Okay, so this is where the original construction of Zuckerman and later construction of Bernstein tell you a way to go from here to here, and they're closely related. So I'm going to define these in a moment. Okay, so I'm going to define these in a moment, but you see that just thinking in this way, if one would like to just think of these functors as tensoring up or taking HOM, then it would be nice to have a ring theoretic description of this category. Okay? And the thing is, there is, and in terms of the Hecke algebra, which was mentioned in the first lecture of the conference, that is in the Deepedra mentioned, the Hecke action from Jackie Langlands. So now I'm going to introduce that Hecke algebra, and I'll state the theorem that the category of, suitable category of modules over that algebra is the NGK. Okay? Okay, so clearly I won't get time to discuss many things, but let's say I have K. So I have a GK pair. Okay? This is a pair, namely that okay, so what we've been talking about all this time. Right? So the natural thing to consider is the following algebra, let's say just for K first, which is E prime of K. So this is compactly supported distributions. On K, which are which are K finite. On left or the right, it does not matter. Left and right are equivalent here. Okay. So let me just, I don't know if I should say anything about this, but this is after all, the continuous linear dual. Okay, so some quick thing. So if you have say a space, a manifold, one has C infinity X. This has, I guess it's Frechet or something. I mean, anyway, it's I don't know what Frechet means, but certainly it has a topology defined by semi-norms, and it's locally convex. And in this, let's say X is compact, it's complete also. But even if X is not, I don't know. Okay, so this has a topology, and one can continue, and one usually defines this to be the linear functionals on that. Okay, so those are compactly supported distributions. So I'm taking C infinity, not C infinity C. Those would be just ordinary distributions. So these are the compactly supported distributions. There's a notion of support for compactly supported distributions. I won't go into that. But the point is now that if X is a group, yeah, it doesn't have to be compact, but if X is a group, then one has the multiplication map, and one can push forward distributions simply because one pulls back smooth functions. So dually one can push forward distributions, and this defines the convolution of distributions. Okay, so there is some point here that if I have two distributions on K, there is a unique distribution which has the obvious property with respect to functions of the form F tensor G, namely you apply S to the first one and T to the second one, and that's the value. And I don't know, Fubini's theorem or something tells you this is good. And that defines a distribution on K cross K. And now you push it forward, and that defines this. Okay, so this is for S and T, so S will be in E prime of K, and T will be in E prime of K. Okay? So the point is that the distribution algebra is a E star, E prime K is a convolution algebra. Sorry, so I said here I meant to say the K finite vectors here. Okay, so this is already a convolution algebra. It's an algebra.
You are taking distributions on G which are compactly supported on K.
Okay, at the moment I'm just taking RK, and then I'll do the pair case separately. So first I'm just doing K. Yeah. Actually, it doesn't matter because I won't be able. I was hoping to do proofs of the elementary properties of RK and then just say GK works similarly, but I won't have time to do the proofs anymore. So. Yeah.
So, here in this diagram, the
Yeah.
one, the upper one, that's second, that is in the parabolic or is it the
G. I'm just breaking up. I want to change both the parabolic and the group, so I'm doing it first. I change them. I want to change the Lie algebra and the group, so I first change the Lie algebra, then I change the group also.
down there?
Yes, sorry, that should have been G. Thank you. Of course, any reasonable construction, it shouldn't matter, well, at least at some stage. Okay, so we'll see. That was a motivational diagram, so I'll leave it there. Okay. So, by the way, notice that the identity of this algebra is the delta function distribution, the delta distribution is the identity, and that is not in the K finite groups. Okay? So this algebra is not unital, because I can't move the delta distribution around and remain inside a finite space. That's obvious, right? So this is not a unital algebra anymore, this is a unital algebra. And so what one does have is that this has approximate identity, an approximate identity. And it has a very nice approximate identity, which is the following, which is a collection of, given by the collection of characters, right? So I look at, say I'll call them chi A. So A is any finite subset of representations. And chi A is, so A is any finite subset. Okay, so chi A is the sum over, say, tau in A of the following this thing, which is the dimension of tau divided by maybe the volume, and then the character of tau star key. Okay, so let me explain. This is a distribution on K. Compactly is about a distribution on K. Okay, namely, you integrate. What is meant by this is you fix your hard measure, you integrate the character of whatever your function is, you integrate it against the character of tau star, and then you use this normalizing factor. And this is the sum of such things. And as A runs over all finite subsets, we get this collection of things. So what is the point? Why do I call it an approximate? Okay, it's an approximate identity. Okay, but it's not indexed by an integer, but this thing. So the we will consider approximately unital modules. Okay, so M, an RK module, is approximately unital if for all elements M there exists some A such that chi A times M is equal to M. Okay, so the point is that these are directed, so they form an approximate identity in the obvious sense. They are directed by the inclusions among these finite sets. Okay. So, and the category of approximately unital modules is an abelian category. It's a good category in which you can do whatever ring theory you want. It's just that things are not unital. Okay. So then one has the following proposition that the category of okay, so maybe I'll just write it this way. Locally finite, k-finite modules, locally k-finite representations is equivalent to the approximately unital R modules. Okay, so actually I don't need to say locally k-finite representations because we have a notation for this already, which is that I just take mkk. So the definition of, if you took G to be k, the definition that was given then was actually locally k-finite modules, right? So this is equivalent to this. Okay, so let me just say what this means. So this is a k representation. So it's hardly surprising that given a k representation, you can extend it to a representation in the standard way of the distribution algebra, and then you can restrict to the action of Rk. And the fact that this has already got some k-finiteness built into it is what makes sure that you land in approximately unital modules, and then it's elementary to show that this is an equivalence of categories. Are there any questions about this? I mean, I'm leaving several things out. Okay, so I'll just remark that this is basically just the same. Once you choose a Haar measure, this is choice of dk. This is the same thing as the convolution algebra of smooth functions, smooth k-finite functions on k. Namely, every such distribution is actually just like a function. So this requires, and it's elementary, it requires a little work. Okay. And one first proves that actually, right. So one first proves that here, okay, it doesn't matter what one proves. Okay. So, I should have said that what I'm going to talk about, say about cohomological induction, there are two references. One is a book by Knapp and Bogan where everything is stated in painful detail, but thorough detail, and there are extensive appendices about distributions and all. And some ways, in some places, more efficient version, and certainly in general more easier to get readable. There is a book by Pang and Panzet. Okay, I think there's an accent somewhere, but I don't know how to put it. Maybe this. Is that right?
Yes.
Oh.
And there is one on C.
Ah, okay.
Yes.
Okay. So this is both these are books. So this is called Dirac Operators in Representation Theory, and more recent. And this is an older book called Cohomological Induction and Unitary Representations. So, for example, this Hecke algebra, all its properties are treated in great detail in Knapp and Bogan. Okay, so now I was going to say that for GK, a pair as we have here, we just take the corresponding happy algebra, which is what appeared, I suppose, first in Frankie Lyman. So K bi-invariant, K finite. So distributions on G, supported in K, and K finite. Okay, so it's just if you look at the inclusion of K inside G, then it's just all the things it's just I R square R of K in this case. Okay, and this is again a convolution algebra. It has an approximate identity, which is the same approximate identity. I just consider those as distributions, the characters of K giving distributions on G. Okay, and this proposition is continues to be true. So I'll just state it, maybe upgrade it to the proposition. MGK is the category of approximately unital GK modules, RGK modules. Okay. Now there is a slight. So this is good. So this is what we sort of wanted. We wanted a module description of the categories involved, so that we can use tensor and Hom functors. There's one. Okay. So there's one problem which I'll mention in a moment. So in the case where GK comes from a group, it's not too hard to show that this, at least as a C vector space, is isomorphic to the distributions on K finite distributions on K, tensored with the universal enveloping algebra. Right? Universal enveloping algebra gives derivatives of the identity and so distributions, and you have to tensor over UK. Okay? But this is not an algebra description. This is a subalgebra, but that's not a subalgebra. And of course, you can also exchange the orders if you want. Okay, so any one of these K-finite distributions has can naturally be written in the basis of just K, distributions on K, and then the universal enveloping algebra, for which we of course have structure theorems also. Okay? So, okay, so anyway, this theorem is true, so I'll say one more thing. In general, one doesn't have, so the situation one wants to treat actually is not just ML and MG, but you want to go through intermediate spaces. But you see, this is not of the form that I have a real reductive group and a compact subgroup, because this is not a real reductive group, the Lie algebra of a real reductive group. So one has to have a slightly more general definition, but the idea is very simple. The idea is you just take, so generally, so I implicitly assumed my pair here came from a group, but you can just treat any pair, including Q, L, C, and you just take this thing. Each of these is an algebra, and then you write down the multiplication that you get from the pair case, and then you just see that multiplication rule works in general to make this into an algebra. Okay, so I'll just say that has to be done. Okay, that's very elementary. There's nothing to do. Okay, and then this theorem continues to go. Okay, so here this GK pair is now allowed to be included in those cases. So the category of approximately unital RK modules is exactly what we have in G. Okay, so now we're sort of in business in the sense that now this implies that we can define tensor and Hom functors. I will define them in a moment. Okay, so yeah, maybe I should just go ahead and define them now. Okay, so maybe I'll just yeah. How do we show that it's? These are characters, right? No, I mean, it's anyway the group is compact in this case, but their K finite is because they're connected. Okay. Are there any questions about what I've said so far? I have a small question. When did I start?
45.
So, okay, 50 minutes. Okay. So, yeah, it's these, the proofs of all these statements are really quite elementary, but they would take far too much time. Okay, so now, of course, this means, let me make a definition here. I mean, this is the obvious definition. Okay, so I'm not actually going to write down the morphism of pairs. Let's say from HL. So I hope there's no confusion. Don't confuse this with the LC that appears there. This, okay, J. Is what you think it must be. So meaning I'm not going to. So this is the formal definition. Meaning, so what do I need to have? I need a Lie algebra morphism from H to G, a homomorphism of compact groups from J to K, and the compatibility which was involved should, well, that's enough actually. Right? Those two should be. You need to, of course, say that. You see, in the GK pair, K was acting on the Lie algebra G, here J was acting on the Lie algebra H, and so the two maps should intertwine those actions. Okay. So, given a morphism of pairs, okay, I will define two functors. So, define P, let's say P, which depends on all this thing, P, which is equal to. I'll write the formula and then see what happens. And I. Okay, so P is supposed to be, both of these are functors from M H J to M G. Okay, so the first functor is just now. So now what does this mean? So it's obvious how to consider RGK as an RHJ module. Just use the morphism of pairs, and the same is true here. Okay. So here there's maybe a small point that I'm taking I'm using the left module action, but I have still a right module action of RHJ on RK, and that converts this into a right RGK action on here. So I've used up one on one side, one on the other. Okay, so that's that. Right. So this is some version of the Bernstein functor, and this is the Zuckerman. I may not use this terminology because there are too many slightly different things are called by these names. Okay, so notice that this functor is a little trickier than this functor because one has to. So what does this mean? So this has a surviving RGK action. Yeah, I should explain this. As I said, you use one of the actions to take the Hom, and then there's a surviving RGK action on the other side on this. Then correspondingly, by the equivalence of categories, that's approximately unital, so that is a GK module, or it has the action of G and K, and then I've taken the K finite vectors. Okay? So here the problem is that this is a straightforward change of rings functor, but this has this extra K finite. And I think the point was historically Zuckerman defined this or the analog of this, and this is actually slightly trickier to work with because of that. And later Bernstein defined this and showed that they are slightly similar. Okay, so I'll just state the following lemma, which is the key to all the properties of all these things, which is that I.
Taking K invariance is an exact functor.
Not always. Here. just taking k invariants on GK modules.
Like that.
Like this, no, it's not always exact, no, need not be. I mean, it's not just exact on k modules. I mean, no, k invariance is exact on k modules, because my locally finite k modules are semi-simple, so there's no problem with that. It is on G modules, yeah.
You're taking G modules.
Yeah, we're taking G modules. So you see, it's
And
like,
then decay finite vectors is not exact.
This is not exact. That is the tricky here, yeah. So that's right. So this is supposed to be doing, let's say we're in the, this applies to all pairs, so say we're in this last step, right? So you're not changing the G structure, but you have a G this thing and you're taking k finite vectors, they need not be exact. Need not be non-zero also, right? Because k is bigger than that. Okay, so the lemma is the following, is that P, okay, so there are two statements. So one is I is right adjoint to the forgetful functor. Okay, so there's a forgetful functor which simply takes a GK module and just restricts it as an HJ module. As a corollary, this means, but once it's right adjoint to, which is obviously exact, this is exact. So once something is right adjoint to exact functor, okay, so let's write this what this means. So there are in Hom, H, J, let's say forgetful functor F. Okay, so that just is the forgetful functor. So it's right exact, it's right adjoint, so there is Hom from whatever one calls V, X is Hom. Okay, so in this thing, V belongs here and X belongs there. So this implies that it is left exact and takes injectives to injectives. And the duals, the other statement is that P is left adjoint to another functor which I'll define. Okay, so there is a similar thing. I want to write it down. So, and that implies that it is right exact and takes projectives to projectives. Okay, so this is the Frobenius reciprocity, right? So just to say, one might naively hope that P. So I is right adjoint to forgetful functor, and one might naively hope that FP is a left adjoint to the same forgetful functor. So that's not true, and that would be too simplistic. And so this, but the proofs are not hard at all once I define F. Okay? These are just formal facts, right? If it's right adjoint to an exact functor, also exact. And so the left adjoints will be right exact and preserve projectives. So these, this is all standard, elementary facts. Right? So if you've seen projectives and injectives, you've seen these things. Okay, so what is the F check functor here? F check of, so given a GK module, let's call it V, I want to tell you what this is, right? So this is like, okay, so first let me define F check, FV. So it's the obvious forgetful functor, but it's also the result of tensoring GK over itself with itself. So therefore that suggests what f check should be, this should be the Hom function. Except that now, here I take j invariance. Okay? So these are the two forgetful functors. This is just a forgetful functor. So here again I use the fact that there is two rj key gk actions and then I take j invariance. Okay? So this is my forgetful functor. So just to clarify what's going on here is that to make this into an RHL module, the Hom space, I'm using the right action of the RHL on this.
In the lemma, the Hom they are not clear.
They are not what?
I guess when we are defining the
No. So this I want to define functors. I want to discuss the adjoinness between these two functor categories, right? So it's just the Homs in those categories. So when I write Hom HG, like HG, I really mean Hom in the category MHG. Okay. Okay. So there's a lot to be said here, but it's all elementary. So and it takes time, so I won't say so much about it. But we'll say one thing that follows immediately from this. By the way, this is just a okay. So I should have said that I'll explain some special cases, and then it will become clear what's going on. So. Coming back to what I was saying here, so if you look at, so there is, of course, these functors can be defined for any pairs, right, morphism of pairs. So obviously there are functors from here to here, etc. And there's the obvious compatibility, induction in stages you would call it, or something like that, or tensoring in stages. All these things become immediate from the formula, right? Okay. Oh, sorry, this is not h equal to cartan. This is just an h. Sorry, yeah. So that was for the when I restrict to theta stable situations, h and I shouldn't have used h. H is not cartan; it's arbitrary. It need not even be. It's any morphism of pairs. The point is these exist quite in all generality, right? I'll show you some special cases, but eventually we'll only want Lewis subgroups, right? So I'll say in a bit how these functors are related to what one wants. So you see, so there are lots of, so let me just make a remark which is important, but I don't have time. So we can take the case, suppose now I'm in GK. Then there is a trivial morphism of pairs KK to GK. Okay? So this is the obvious morphism. So that means I have functors back and forth from these things. On the other hand, this is a semi-simple category, so it has every object in fact is projective or injective. Okay? So that means that in applying any functor, any object, both this P of any k finite module, so V here, this is therefore a projective in that. Okay? And IV is an injective in that. Okay? And if you think about it for a moment, this has a natural map to V, and this has a natural map from V, and these are injections and surjections. Okay, so just from the adjoinness properties, we've immediately shown that GK has enough injectives and projectives. Okay, because it's true in KK, and then you just apply this properties. So this discussion implies that MGK has enough injectives, projectives. Okay, so this is slightly inexplicit, but one can write down explicit resolutions by injectives and projectives, and that's useful sometimes. Although Draven doesn't believe it should be done. So, okay. So there are natural Kosovo resolutions one can write down in the sense that there is every object in MGK has a standard resolution, one by injectives and another standard resolution by projectives. But the point is it's all coming very cheaply, so to speak. Okay.
And the trivial module varies sometimes.
Yeah, so the Kosovo resolution for a trivial module essentially can be made sense of here. Right? Just like in UG, I mean the same works for UG, right? So you can basically resolve the trivial by, okay, and the same proof. Yeah, so again here is an instance where the proof in Knapp and Bogan is extremely long, when it really requires only 3 or 4 lines to say you take a certain gradient and then you use the standard exactness of the abelian Koszul complex and you will get the. So there are simplifications. I think that may be marked in farming plans. Okay, so this implies also that we can derive P and I. So you have derived functors, the left derived functors of Pj, which would be normally called Lj, let's say, which are just called Pj for j greater than 0, and the right derived functors of I, which is called I sub I up to j. Okay, so let me just remark on what is the advantage of maybe unnecessarily doing this in thus generality, but there is some advantage. So one case is that you can take the trivial pair, that is the group, identity group and the zero leader. Then Ij of W is the ith GK the jth GK cohomology of W, and P's lower j of W is the jth homology of W. Okay, this is just immediate, because if you look at what this means, so let's just look at what this means. So I is the map to the trivial group, so that means I is actually just the GK invariance and P is the GK co-invariance. So the derived functors are what you say they are. Okay. The other important case, which is important for us, is I didn't introduce this, so I don't have to say that. So the other important main case will be for us will be theta stable. Okay, so there are several. I'll just now have maybe time to state the main theorems about these functors which give the construction, and they will require some positivity assumptions and things like that. So henceforth the pair we consider only the inclusion of pairs coming from a theta stable parabolic. So this now is the notation. Okay, this is just to simplify things. Okay, so actually, there are several theorems. So there are the main theorems. I will say there's the dualities, which are actually general. Meaning, now when I'm saying general, I mean actually apply in that setting rather than this. Then there is the irreducibilities and unitarity. So these are the main theorems about these. Okay, and I'll just hopefully state all three of these, and then that will at least give us a formal construction of this. Okay, I think I have about 2 minutes more that I can spend on this setup. Let me tell you.
Before you raise, much of what you did is independent of reductive and compact.
This part is all independent, right? Approximately this equivalence. The definition of the functors is perfectly general, right? For any morphism of pairs.
You are going to use it for parabolics
which are not reductive, yeah. And in fact, as I said, so I definitely going to deal with that. So the only wrinkle is that you have to define this thing properly, right? I mean, it's a very minor thing, right? You have to define RGK using this tensor product and then write down the formula for the convolution.
K is always
K is always compact.
K is always
K is always compact.
So people talk about GH modules.
Yes, so, okay, I have to,
No, people talk about GH modules instead of GK modules.
Yeah, you can do it. I mean, this is a nice way of doing this. So okay, it's compact, but you can do slight variant without your favorite version of Heck algebra, and then you can take the group is any algebraic group. You lose some things. For example, this projective argument uses.
I mean, this existence of projectives and all used, the fact that this is a compact group essentially, right? This category was semi-simple. So, I mean, and we use that. So,
Right.
so anything was projective.
There are enough injectives so that you can define this as Zucker parameters.
Okay, so I'll just hopefully get around to stating these three theorems. So, okay, maybe I'll just say what the theorems are. So, the duality theorems are of two kinds, okay? So, there is what's called easy, or I think of it as, it's just linear algebra. Okay, maybe a remark which might be clarifying for some is that, when you discuss in topology, there's the linear algebra duality between the homology and cohomology of the manifold. Namely, at least with field coefficients, the cohomology is just the linear dual of the homology, right? But then there's, for manifolds, there's Poincare duality, which relates things in different degrees, okay? So that's the harder duality. So just like that, here there is a easy duality, I think it's, so the easy duality statement is the following, that essentially, okay, so there is a technical point which I had not discussed here, but I'll leave it completely aside. If I take a module and I take the contragradient module, so now this is a bit careful, you have to take the Hom into C and K finite vectors. So this is the K finite contragradient operation. So let's assume we know how to do that. And this is the same thing as or equal to Pj V okay. So this holds in fact in any setup. And there's the harder duality, which is Zuckerman or Poincare duality, which is that this is a little more. So as you know, in Poincare duality you have to fix something. So let me now assume that I'm in a situation where I'm going to assume I'm in this situation, but it applies not in all generality, but in some generality. So this is the dualizing object, right? This is the dualizing sheaf, and it says that Pj of this is isomorphic to I of m minus j of v. Here m is the dimension of the space. Okay, so this is the fundamental class, so to speak, right? So Pj and Ij are related in dual degrees by some operation involving the fundamental class. So this is called Zuckerman duality. Okay, so just for those who are familiar with some of these cases, then in the case of GK cohomology, the first one restricts to some stupid thing, just linear algebra duality. The second one restricts to actually Poincare duality for GK cohomology, which is, of course, in Borel-Waller and places like that. Okay. So these two are the duality theorems. For the other, so this is quite general. For the other two types of theorems, one needs some sort of positivity. So here, this is of course going to be, after all, we are trying to generalize Borel way and things like that. So we better have some statements. Okay, so maybe I'll just state them. So I need to discuss some. Okay, I need to discuss the good length of whatever it's called. Okay, so if. Okay, so I'll come back to these two theorems. I'll just state some two relatively elementary facts. That one, if C in ML LC has infinitesimal character, C lambda, then Ij Pj have infinitesimal character so I'm going to define this. Okay, so I'm in a theta stable setup. So Q is L plus U, and rho U is the half sum of the positive roots occurring inside Q. Okay, so the thing to notice, of course, is that L contains a Cartan subalgebra. So the infinitesimal characters of L are parameterized by points of the dual of that Cartan subalgebra modulo some while the while loop of L. Okay, so we can in particular, so it's like H star. Now H is the Cartan modulo WL, so we can just map it to H star modulo W, which is our space of maximal ideals of characters of the enveloping algebra. So therefore this lambda is thought of there, just like that. And then I can just take the half sum of positive roots of the Cartan in the unipotent radical there. So this is the, sorry, so this is not correct as stated. Sorry. This is, okay, so, I forgot something. Okay, so maybe sorry, I forgot to, I'll write something down and then I'll tell you what they are. Okay. Okay. So yeah, so the point is now, okay, so when it comes to the unitarity theorems, one has to do something. So so what might you expect? Okay, so what do you expect? You might expect that if you start in the irreducible module, it remains irreducible under some positivity conditions, just like happened in Borel-Way on some generalized sense, and similarly for unitarity. For irreducibility, that's okay, but for unitarity, you have to introduce a shift. Okay, so I'll define these two. These are the actual cohomological induction functors, and Lj of V is actually Ij of Lj is Pj V tensored with the top exterior power of U. Top exterior power of U. So this is a change of normalization. Okay, so with this, with this normalization, namely, so now let's understand what we're doing. We're applying Pj. Okay, so writing out a notation takes forever, but we're applying Pj to the module V tensored with the top exterior power of U. This is being considered as an L compact module. Then we are going straight all the way to Gk. Similarly here, as I said, but didn't write down, these inductions can always be done in stages. So one can think of this as first going from L, K intersection L to Q, and then to G, and then change at the last stage change the compact, and similarly here also. Okay, it's with these facts that these have the infinitesimal character lambda plus. Okay, that's that. Then let me state the two other theorems quickly. So say Z inside MLLC has infinitesimal character lambda. Okay, then say lambda is good if the real part here. So now we fixed something. I'll write it down. Okay, and weakly good So for every root space appearing in the unipotent radical of L, we should have that what is going to be the infinitesimal character pairs positively, at least in real part, with that alpha. Okay, so it is exactly a positivity condition, and it's weakly good if this is true. Okay, if it's a weak inequality. Okay, so then the theorem becomes theorem. So these theorems, I suppose, are due. This is probably due to Knapp and Bogan or Bogan-Ribby. I think Bogan, is that if lambda is good, then okay, so there are several statements, Lj of V and Rj of V so there is this special number which is the dimension of U intersection K. So you get vanishing outside those degrees, and in fact these two modules are the same in that degree. And so there are three statements here, and it is irreducible and non-zero. Okay, and everything is true if it's weakly good except the non-zero part. That may be false. Okay, so this is the irreducibility theorem. So what it says is that essentially all these complicated functors you defined actually live in a single degree. So it's just very much analogous to Borel wave. I'll say more about that. And it is irreducible and non-zero in that degree if you're in the weakly good range. Okay. Okay, that's okay. I'll take 5 minutes more. That's okay. Okay, just as an aside, this dimension U intersection K, so that is dimension of U intersect with the compact Lie algebra. So, for example, for SL2, for the example that we have, well, U intersection K turns out to have dimension 0, right? Yeah, and so one doesn't have to do anything really, but it doesn't matter. Okay, that's, I'll say more about this. This is anyway the correct, okay, so for the, just to relate to what I was saying about geometrical things yesterday, G model is kind of non-compact, and it looks somewhat like a Stein manifold, but it's not a Stein manifold because it contains this compact complex manifold. And this has dimension exactly equal to this. So there's no direct parallel, there is, but I'm not able to say it right down now. But the fact that these are vanishing outside degree J is somehow reflecting this is as Stein as possible, as it is possible for it to be. Okay, that's just a throwaway remark. Okay, so remark is what happens, of course, everything we should be doing should also apply to the compact case, right? So how does this work? So in the compact case, I don't have time to say, but this reduces to giving you back the Borel wave theorem, okay? Well, it gives you back Borel wave, not, well, Borel wave is included in the formalism, but this theorem will give you back Borel wave. Okay. The second theorem is the unitarity theorem. If lambda is good, then okay, Z unitarizable implies Rj Z or Rs, which is equal to Ls by the previous theorem, irreducible. We know it's irreducible and it's also unitarizable. Okay, so basically these two theorems more or less give you a large supply of irreducible unitary modules. And if you take the case, so the point here is that these generalize. So in particular, so if Q is theta stable, and I take lambda a unitary character of the L group, the Levy, I get a module which is the AQ lambda, which is either Ls of C lambda or Rs of C. Is irreducible, unitary. Okay, and this part I have not explained, and it's cohomological. So next time I'll maybe explain that. Okay. So the point is that these are the general theorems about how these functors preserve irreducibility and unitarity. There's also basically from Frobenius reciprocity and just some homological standard machinery. You also get a spectral sequence which will compute the GK cohomology of these modules, and it's very easy, more or less directly follows from that these will have cohomology, GK cohomology. So just to tell you what the answer is, and maybe I'll say something next time, the cohomology of AQ lambda is isomorphic to the cohomology of the compact dual of L modulo the compact dual of L intersected K, which in K is contained as well. But let me write this. Okay, with a degree shift. Okay, so this I'll discuss it next time. Okay, so yeah. Right, okay, I think that's all I wanted to say today. Are there any questions? So I forgot to say one part, meaning which I don't have time for, but let me just say something about this. So our basic idea is to look at this sequence of functions, right? So let's just look at the top sequence.
When you define the
Let me just say what I got to say. So if you think of, you can take each of these is a P functor, P or, well, your choice, P or I. So there's a P also, right? But at each stage you can take an I functor for the pair, for this pair. This I functor was first introduced by Zuckerman, and I'll just say what it is. It just says take a LC module, so remember LC is L intersected K, and then just take its module of K, its subspace, maximal subspace of K finite vectors, meaning the maximal subspace on which the action of the Lie algebra of K actually exponentiates nicely to an action of the Lie root K. That's the problem that we know. There may be no such vectors. It's easy to give examples. So therefore, this functor might be vanishing, but then it has derived functors. And those are what are giving us something non-vanishing. In the other direction, you are sort of looking at the same thing, let's say Q bar. It's in this Q bar business, don't worry about it too much. It's not, it's important for the unitarity and all that. The other way to look of the P way to do things, so this is P, is, okay, the rest is, I could write, these functors are just, so remember that the basic idea is this is an inflation, that's not a problem. This is a tensoring up on the UG action, and then you're taking the largest K finite subspace. So here you might think that you don't tensor up, but you take the form from UG, which is okay, and then you might take the largest K finite portion, but that doesn't exist. So that's the difficulty. It's not meaningful to talk about largest K finite portion. Easy example to show you that. Just already look at S1, right? So then the point of this whole discussion with K finite distributions and the reinterpretation of that is it gives you the right way to talk about K finite portions. That's what this thing is. So this is just a remark related to it. So this is the traditional Zuckerman functor, and it's usually denoted gamma. And this is denoted pi, if I remember. Okay. And then there are other functors. Okay, so it would have been nice to explain how gamma is related to taking sections in the vector bundle picture, but it's all written down at great length in apps, so I suggest you read it. Okay, yeah, sorry.
So, when you were finding the right functors for I from Zuckerman, so at the time you had an inclusion I from GK to 0 I.
Yes.
Where will you use that?
As I said, if you look at that's not an inclusion map. It's just zero map.
Yeah. Oh, yeah.
Yeah.
It's a 0.
So if you look at the P and I functors for that, it gives you back GK cohomology and GK cohomology, if you're familiar with these things. It's just then it's just the derived functors of invariance and coinvariance. Right? Just like group homology, derived functors of invariance and coinvariance. So the point is that these definitions contain many others other functors, so that's convenient. And you see, anytime you compose two of these functors, some of them, okay, so yeah, I should have said, sometimes it happens that they're exact, right? So for example, in this case, the one usually uses a co-induced construction at this stage. Okay, so I won't say what that is exactly, but well, it's like a Hom, as I said, it's Hom of UG into the module and then K finite, LC finite vectors. This is exact, but this is not exact. So when you derive the composition, you are just deriving the second one, right? Similarly, in the other way of doing things. So some of these functors are exact, some of them are not exact. But then anytime you have to compose two, you have your spectral sequence relating that, right? So you have, I mean, the point is somehow this uses, all the homological algebra one needs is in place once to do what calculations one wants. Okay, so next time I'll discuss cohomological representations, maybe show that this construction yields cohomological representations, and then discuss what is the main idea behind the proof that these are all representations.
Now let's thank Arvind. Late for lunch.